Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 11.1.2, which is the volumes of similar solids. And so what we're going to determine today is similar to how when we saw area scale factor be affected by linear scale factor. Today we're going to see what happens when we have a volume scale factor being affected by linear scale factor. And I think if you remember the area lesson, then the volume should be somewhat predictable, the result anyway. And so it says in 11.1.1, we began a study of surface area and volume of solids. We're going to continue that investigation in order to generalize ratios of similar solids. So it says, describe the solid formed at the right, and what are its dimensions, length, width, and height. Let's go ahead and just describe it real quick. We know it's a rectangular prism. And then we'll find out its dimensions. And I know it's a rectangular prism because if you look at these darkened breaks right here, that's where you're going to fold your figure if you were to cut this thing out and actually manipulate it. So it looks like we've got dimensions of, looks like 3 across, 4 going up and down, and then it looks like, you see how this thing here would fold upwards? That makes me believe that it's actually too high. So if I was to do length times width times height, it would be 3 times 4 times 2, or 3 by 4 by 2. That would be the dimensions of this rectangular prism right here. So now it says, have each team member select a different enlargement from the ratio of those below. On graph paper, carefully draw the net of a similar solid using your enlargement ratio, then cut out your net and actually build the solid. And so what I'm going to do is I'll go and just select, because the one is pretty obvious. I mean, we're going to find out its volume. We're going to get the ratio of volume. So we can actually do that right now. So 3 times 4 is 12 times 2 is 24. So the original volume would be 24 units cubed. If I was to do a new volume, in other words, a scale factor of 1, everything would stay the same, right? So that would be 24 units cubed, and then 24 units cubed for their ratio. It's when we get into this scale factor of 2 that things are going to get a little bit more tricky. 2 instead of a side length of 3, I'll probably have a side length of 6. So 1, 2, 3, 4, 5, 6. I'll go and just space them out because I don't have graph paper available to me. Instead of 4, it'll go down 8. So 1, 2, 3, 4, 5, 6, 7, 8. So I'll go and just connect those 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, 7, 8. Pretty much almost there. And then this guy here, that's 2. Remember, we're scale factoring 2 here, which means it'll go up by 4. So I'll go ahead and actually change colors. That way you guys can tell the difference. 1, 2, 3, 4, and then he'll still go 8 down. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 1, 2, 3, 4. Again, with graph paper, it would be a lot easier. And then all the other sides would grow in tandem. So let me see here. So this guy would grow up by 4. So 1, 2, 3, 4, and then he would connect. And then 1, 2, 3, 4, and then this guy would grow up by 4. So 1, 2, 3, 4, and then connect. 3, 4, and then it would go, and I apologize, I'm about to blast into part D here. Let me just move him. Let me just move him down just a little bit here. Move you. And I apologize if this creates some visibility issues, but 1, 2, 3, 4, and then 1, 2, 3, 4, and then another one going out 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. And then connect those down. So that's what the net would look like, but actually it doesn't, like some of these miscellaneous pieces wouldn't really matter as much. All you have to remember is that when you scale factor by linear, your original side lengths, which are originally 3 by 4 by 2, would all just get almost amplituded up by 2. So then you would end up with a 6 by 8 by 4 figure. And what happens when you do a 6 by 8 by 4 figure is you end up with a new volume of 192 units cubed, whereas the original was 24 units cubed. Now, if you look at the ratio of the volumes, if I go from the original to the new, then that's going to be a ratio of 1 to 8. 1 to 8 right there. Okay, so let's see if we can come up with some kind of pattern here. If we enlarge everything by 3, and so enlarging everything by 3, again, I'll go back to my original 3 by 4 by 2. Again, you're supposed to be kind of making these figures as a team, but we'll go and fast forward it. If I enlarge everything by 3, that's going to be 9 by 12 by 6. And so what happens when I multiply those guys together to get volume? I'm going to end up getting 648 units cubed as the new volume. Of course, the original volume, right? The original volume actually will always be 24 units cubed, right? This is always the original figure here. So we can actually fill that part in pretty quickly. So again, let's go and look at the 648 divided by 24, and we'll end up with a volume ratio of 1/27. And I'm hoping by now we are seeing a pattern between linear scale factor and volume scale factor, and so hopefully with this next one, you might not even need to come up with a new volume here. You might know that this is 1/64, right? Which means if you just took 24 and multiplied it by 64, you would very likely get the volume you're looking for. Now, let's just see if this is true here, if it ends up being 1536, because, you know, sometimes I'm pretty good at being wrong. The original is 3 by 4 by 2. So now this will end up becoming 12 by 16 by 8. So what is 12 times 16 times 8? It is, in fact, 1536. So now the new volume will always be 24 times, looks like the scale factor being cubed, which means the ratio of volumes would be 1 over the scale factor cubed. And again, if you decide to go from large to small, then that means that you're gonna have 8 over 1, 27 over 1, 64 over 1, and r cubed over 1. But it doesn't really matter which way you go. So as long as you stay consistent. So hopefully the pattern is starting to make a little more sense after this table here. And in part D, it says, how does the volume change when a three-dimensional solid is enlarged or reduced by a similar solid? For example, if the solid's length and depth and width are enlarged by a scale factor of 10, then how many times bigger does the volume get? Well, we saw this. Well, since the scale factor in part D is 10, that means that the volume would be enlarged by 1,000. And that is because if the linear scale factor is equal to r, that means that the volume scale factor is equal to r cubed. And just because we're here at scale factor, I'll go ahead and just remind us all that the area scale factor is r squared. All right, give me a second. I'll be back with the next problem. I'll be right back. Here we are in problem 11-16. It says, examine the 1 by 1 by 3 solid at the right. And so I'm going to go and put those dimensions in right now. One of the things you guys want to make sure that you guys are clear about, because it can be confusing, is that this is not a 1 by 1 by 3 because each of these depth pieces is 1. Each of these depth pieces is actually 3. All right, so just make sure. So this is a 3, this is a 3, and this is a 3. So it says build the blocks using the E tool. So actually I pulled that up and it looks like this. If it was standing up, it would look like that. And so we're going to try and build this shape here in a little bit here. It says if the shape was enlarged by a scale factor of 2, how wide would the new shape be, how tall and how deep? So in part B, if the linear scale factor was 2, that means that a 1 by 1 by 3 figure would then be 2 by 2 by 6. All right, so that should be pretty straightforward, I'm hoping. If we are asked in part C, how many of these 1 by 1 by 3 solids would you need to build the enlargement in part B? Use blocks to justify your answer. Well, remember, our linear scale factor is 2, right? Our linear scale factor is 2. So we would imagine that our volume scale factor, right, which is the number of blocks it would actually take to fill all the mass inside, our volume scale factor should be 8. So I'm hoping that when I show this diagram, it will take 8 blocks. It will take 8 blocks. Okay, let's find out if that's true. All right, so I'm going to go to this E tool here. So now it's 1 by 1 by 3. So now that is one block right here, right? So now I'm going to go ahead and enlarge the scale factor by 2. So that means that it's going to go 3 more up, right? So that's going to be 4, 5, 6. So now I have 2 of those 1 by 1 by 3s, but now I need to lengthen this deal here by 2. So I'm going to go behind 1, 2, 3, 4, 5, 6. So I know it looks like I've got a bunch of blocks here. But remember, each 1 by 1 by 3 is actually one block. So I've got 1 going down, 2 going down, 3 going down, and then 4 going down. I just got to replicate it again. 1, 2, 3, 4, 5, 6, and then oops, if I can see that, 1, 2, 3, 4, 5, 6. Okay, so this should make sense here. I've got 1, 2, 3, 1, 1, 2, 3, 2, 1, 2, 3, 3, 1, 2, 3, 4, and then times 2. It actually did, in fact, take 8 blocks to do it. So yes, thank goodness. Took 8 blocks. Boom. Good job. So now, what if the 1 by 1 by 3 solid is enlarged by a scale factor of 3? How many times larger would it be? So if our linear scale factor would be 3, which means a 1 by 1 by 3 would become 3 by 3 by 9. And it would, so if our linear scale factor was 3, that means that our volume scale factor, in other words, it would be 27 times the volume of the other one, based on volume scale factor being the cubed version of linear scale factor. So hopefully this is a good introduction into ratios of volumes. And as always, please leave questions or comments in the comments area, and I will see you all in the next episode.